Something exceedingly unusual is sweeping past our sun. We don't fully know what it is or why it's here. We can't even see it right now. But we've tracked this wanderer obsessively for months. We've named it 3I Atlas and labeled it an interstellar comet. There's a surprising amount we do understand about this newcomer to our neighborhood. In just 4 months, nearly 100 studies have been written on 3I Atlas, and there's plenty more circulating off the official books. Some of it sounds outrageous. So today, we'll strip away the speculation and get to the core of what you really need to know about 3I Atlas. First, the journey. At this moment, 3I Atlas is at its closest pass to the Sun, perihelion. The peak falls on October 29, when the body sweeps within roughly 210 million kilometers of our star. In space science, we prefer a larger yardstick, the astronomical unit, or AU, the average Earth-Sun distance, a simple way to scale our cosmic backyard. 3I Atlas reaches perihelion at about 1.4 AU from the Sun, meaning it never dives especially close, just inside Mars's orbit. Still, this is when activity should spike for 3I Atlas. It's the warmest point, so surface ices will vent and eject material into space. That's normal comet behavior, called sublimation, solid straight to gas in a vacuum, bypassing liquid entirely. Sublimation gives comets their signature, a fuzzy glow and a trailing tail. The glow is gas and dust escaping the nucleus, technically the coma. The tail forms under the solar wind, streams of radiation flowing from the sun's surface, which shove the finest particles outward, away from the comet. It's cosmic choreography at its best. Unfortunately, we can't witness this peak for 3I Atlas because the sun's glare blocks our view. Call it bad luck or something else, our line of sight to perihelion is completely washed out by sunlight. So, we know where 3I Atlas is, and we can infer what it's doing. While we wait for it to emerge on the far side, let's rewind and figure out how it arrived here. That story is compelling. We've tracked 3I Atlas since July 2025. The Asteroid Terrestrial Impact Last Alert System, ATLAS, a worldwide network of scopes in Hawaii, Chile, South Africa, flagged it. Their job is to stare at the night sky and spot movers. On July 1, they did. One more moving speck. It went into the new asteroid bin, and they nearly moved on, until something didn't fit. It was too fast. Everything in space moves, and everything in the solar system orbits the sun, bound by its gravity. Motion keeps us from plunging into that gravitational well. The nearer you are, the faster you must travel to stay aloft. Go fast enough and you climb out of the well. Reach escape velocity and you're free, off into interstellar space, the near-empty gulf between stars. When astronomers measured the newcomer's speed, jaws dropped. It was the fastest object ever clocked in our system. For scale, Earth circles the Sun at 30 kilometers per second. That's us, moving briskly and relatively close in. Mercury, at 0.4 AU, is baked and must whip around at about 48 kilometers per second to avoid falling inward. The Atlas target was cruising at 58 kilometers per second, while it was still far out, just inside Jupiter's orbit, roughly 4.5 AU from the Sun. At that velocity, it would blow past the Sun and keep going. That's a hyperbolic trajectory, from the interstellar void and headed back there after a quick grand tour. That's when the name 3I Atlas stuck, the third interstellar object ever found. You know the first, Oumuamua, our inaugural interstellar visitor, strange but in a very different way than Atlas, and we'll get there. The second, 2I Borisov, tends to be overlooked. Interstellar, yes, but otherwise comet-like, almost boringly normal. If anything, its weirdness was how not weird it looked. 3I, by contrast, differs from its siblings in 3 big ways. First, size. It's simply larger. Oumuamua was up to 400 meters. Borisov was around 1 kilometer wide. 3I Atlas could span up to 5.6 kilometers. Second, speed. Atlas is traveling at roughly twice the velocity of the first two. Third, and strangest, arrival direction. Oumuamua dove in from the north, roughly along the direction our solar system moves through the galaxy. Remember, we orbit the Sun, but the Sun itself orbits the Milky Way center, with us in tow. So as much as Oumuamua hit us, we also sort of ran into it. 2I Borisov did nearly the same, on a more diagonal approach, but still from that general heading. 3 Atlas isn't another head-on, it's a T-bone, slicing in from the side, lined up almost perfectly with the planetary orbits. Our system is a relatively flat disk of debris that coalesced around the Sun, gradually forming planets, moons, and asteroids, yet holding a disk shape. That plane is the ecliptic. Only a few things sit noticeably off it. The most famous is Pluto, tilted by about 17 degrees, sometimes above the plane, sometimes below. That context shows how aligned 3I Atlas really is. It's only 3 degrees off the ecliptic, practically flush with the disk. In 3-dimensional space, an interstellar visitor could come from anywhere. Hitting the disk nearly side-on is a remarkable coincidence. Which leads to a bigger question: where did it come from? We know it arrived from the direction of the galactic center. In the Milky Way's top-down view, we live in an outer spiral arm. The hazy Milky Way band you see at night is the next arm over. 3I Atlas came in from the brilliant central bulge, bright because stars are tightly packed there compared to our neighborhood. But again, space has depth. Flip to a side view. Like our solar system, most Milky Way material lies in a thin disk around the core. But some populations live above and below that in a thick disk. It's sparser there. Fewer massive collisions, fewer supernovae, fewer black hole disturbances, so objects can drift undisturbed for eons. Astronomers suspect 3I Atlas hails from that ancient region, perhaps around 7.6 billion years old, nearly twice Earth's age. We can't likely trace its full origin path, but researchers recently backtracked its motion 10 million years and identified 93 stars it likely passed. The closest of those encounters? About 0.3 light-years, 63,000 AU. Today, 3I Atlas sits only 1.4 AU from our Sun. Now, how did it approach, and what did we learn along the way? Though 3I Atlas was formally announced July 1, its first appearance came May 7, 2025, in imagery from TESS, the Transiting Exoplanet Survey Satellite, which orbits Earth scanning for exoplanets. For about a month, TESS happened to be looking right where 3 Atlas was, letting us trace it through Jupiter's orbital region. Astronomers first measured brightness changes to infer composition. Over that month, 3I Atlas moved roughly 1 AU sunward, so its apparent brightness should have climbed modestly. Scientists use flux to describe apparent brightness. Think of noon sun on a clear day versus standing on Mercury. Same sun, vastly brighter to you. Flux changed, not the sun's intrinsic output. The team expected 3I Atlas's flux to rise 1.5 times between May and June. TESS recorded a 5 times jump, far more light reflected than expected. That told us this isn't an asteroid. It's a comet beginning to shed material and build a coma, gas and dust boosting reflectivity. 2 oddities stood out. First, polarization. Oversimplifying, when sunlight scatters off dust and gas, the direction of that scatter encodes information about the material. Side-scattered light, perpendicular, is called positive polarization. Backscatter, parallel, is negative polarization. Most bodies lean positive, even interstellar ones. 2I Borisov was positive. 3I Atlas registers negative, and not just slightly. It shows the most extreme negative polarization ever observed. That's bizarre. One of many hints that normal is local. What's common here may be odd elsewhere, and vice versa. Second, the very existence of a coma at all, that far out. In May-June, 3I Atlas was still beyond Jupiter, over 5 AU. It's frigid there. Typical comets are still frozen at 5 AU. Their coma usually awaken between 3 and 4 AU, when sublimation really kicks in. That's because many homegrown comets are water ice rich, and water needs significant energy to sublimate. As we turned bigger telescopes on 3 Atlas, we found its coma dominated by CO2 gas. Water vapor was present, but CO2 outnumbered it roughly 8 to 1, the reverse of what we usually see. Think dry ice, theatrical fog from frozen CO2. It's produced and stored at extremely low temperatures. Remove it from deep cold and it instantly sublimates, that telltale plume. That's 3I Atlas at great distance, an early forming coma because CO2 sublimates far below water ice temperatures. As it drew inward, we watched that CO2 to water ratio flip. By late September, near Mars's orbit, 1.5 plus AU, 3I Atlas began venting water vapor furiously, about a fire hose on full blast, more water than expected from a typical comet at that range. We've never seen such a sudden water surge. Metals told a similar surprising story. Over summer, astronomers detected nickel in the coma, but no iron. A few notes: nickel and iron are common, forged in dying stars and dispersed in supernovae, later folded into new systems, so they tend to appear together in planets, moons, asteroids, and comets. Seeing nickel without iron raises the question, where's the iron? What separated them? Also, metal sublimation at that distance is odd, still out beyond Mars in the cold asteroid belt, and sublimation is heat-driven. CO2 needs little heat, but metals shouldn't be lofted so easily. Most likely, the strong CO2 outflow was dragging nickel atoms along. That still doesn't explain the missing iron. Then, like the water, iron finally appeared in late September. The nickel-iron ratio rapidly settled to a more typical mix. So 3I Atlas is trending toward normal, but taking a very roundabout path. Now, tails. Another way 3I Atlas misbehaved, at first. The earliest tail we saw in summer pointed toward the sun. That's unusual. Tails are built by solar wind pushing material away from the sun. Why the wrong way? Likely tied to the early CO2-driven coma. Forming so far out, the solar wind may have been too weak initially to blow the cloud anti-sunward. Material piled up on the warm, sunlit side until the wind strengthened and sculpted a conventional tail, which we did see by September, a short, fan-shaped tail pointing away from the sun. Not every comet has a dramatic miles-long streamer. Tail length depends on composition and distance. Hale-Bopp, for instance, famously displayed an enormous tail in 1997, helped by being much closer to the sun, 0.9 AU, about half an AU nearer than 3I Atlas will ever get, so it experienced stronger heating and a more forceful solar wind. Around then, we got our closest look yet at 3I Atlas. Not from Earth, but from Mars. On October 3, it passed within 0.19 AU of the red planet, its tightest brush with any planet. Lucky for us, Mars bristles with cameras. We used them. Here's a shot taken by Perseverance from the surface. That's how it would appear in the Martian night sky. It's not postcard pretty. The rover's camera isn't built for this. To collect enough light, it used 30-second exposures and stacked several frames. So the result is a streak more than a crisp dot. Another view from ESA's ExoMars orbiter circling Mars shows the object more clearly, but still without enough resolution to separate the bright coma from the nucleus. For that, we'd want NASA's Mars Reconnaissance Orbiter, which carries the most powerful telescope at Mars. As of recording, that image hasn't been released, if it was taken at all. A US government shutdown paused NASA operations until the politics are sorted, which could take a while. Fortunately, time is one thing we currently have. The sun will keep masking 3I Atlas until early December. After that, we can study the solar aftermath. Our closest distance remains about 1 AU on December 19th. By then, 3I Atlas will be outbound, leaving the system. One more relatively close encounter remains. On March 16, 2026, it will pass within 0.36 AU of Jupiter. We don't have Mars-level camera coverage there, but we do have Juno, which has spent a decade studying the giant and its moons. It should get a last look at 3I Atlas before it fades into the dark. At that range, the object will cool and calm, but it may bear changes from its solar heating. That adds a key piece to our understanding of interstellar visitors. It's entirely possible many odd traits don't originate at birth, but are acquired over long, lonely journeys. For now, we can only speculate, but more answers and surely more questions are coming soon. Enjoyed the breakdown? Tap like to boost this video. Subscribe and ring the bell so you don't miss what happens next. Comment below, contact or countdown. Share this with a friend who watches the sky.